In our last class, we talked about what electromagnetic waves do when they hit something, and the answer was they do three things. They might be part of it might be absorbed by the object, part of the wave might be reflected away from the object, and part of it may actually just pass through. And usually it's some of all three. We went on to say that for the absorption and the reflection, that's when the energy and the momentum that the wave brings with it are transferred to the object. So remember, waves transfer energy, we know that. And in fact, they transfer momentum as well. We'll get to that second. We were in the middle of talking about the energy piece. So the wave hits the object and some gets like sort of absorbed in, some gets bounced off, but either way, energy and momentum get transferred to the object. So we had to talk about how much energy the waves have, and one point of view we talked about was how much energy is in the wave because of the electric and magnetic field, because we had connected energy to electric field and energy to magnetic field back in the previous chapter before we were talking about waves. And if you just work out the details, we figured out that actually the electric and the magnetic fields carry equal amounts of energy per cubic meter, so UB equaled UE. So it's kind of like split. The wave has the energy from the electric field and the energy from the magnetic field, and those two amounts are equal, so they add up to twice as much. And then here was a formula for the total amount of energy per cubic meter related to the strength of the electric field. Okay, so but that's the energy that's in the wave, like at any given moment. But we wanted more to the point. We want to talk about the energy that gets imparted to the thing that the wave hits. And there, it's based on time, because if the wave keeps hitting, then there'll be more energy imparted. And also, how big of an area is the wave hitting? That matters too. And so we talked about how you don't just talk about energy, you talk about energy per second and per square meter. So energy per second is power, and then per square meter, so divide by area, that's what we call intensity. And this was all, we talked about this back with mechanical waves, so this part isn't new. Intensity is sort of the right thing to talk about when we're talking about energy going from a wave to a thing. And it's in watts per square meter, right? Okay, so without a derivation, we can connect the intensity of an electromagnetic wave to the amplitude of the electric field. So this is a good relationship, although I didn't explain where it came from. We did a couple of problems. Yeah. Oh yeah, we talked about if the wave is ultimately coming from a point source, then the point source is providing some power, so many joules every second, but then that's going outward in all directions, so that's a spherical wave, and so the intensity is based on how far away you are. What you end up dividing by is 4 pi r squared, which is the surface area of these spheres emanating out from the point source. So this is the intensity from a point source. And then we had worked out this problem. Yeah, okay, so that's a quick review of probably the last 20 minutes of our last class. So now, moving on, what does an object do with the energy that it gets from the wave? Well, so one thing is the absorbed energy, much of it anyway, will cause those atoms to oscillate up and down because it's electric and magnetic fields that are hitting it and going up and down, so that's going to get absorbed by the electrons in the object, or maybe the protons in the object, and they'll start oscillating. And of course that's just random thermal motion on an atomic level. In other words, it's going to warm up. The temperature will get warmed up. So this is how when microwaves hit food, the food gets warmed up. Or just if you're out in the sunlight, you're going to feel warmer than if you're in the shade, because the sunlight is hitting you and increasing your temperature. But there's also a little bit of some of the energy actually gives you overall kinetic energy. So it actually gives you a kind of a push. The object is pushed a little bit, and that's connected to the momentum, which I had mentioned earlier, but we hadn't talked about yet. That's the momentum that the wave is giving you, giving the thing that it's hitting. So yes, on one hand, it's just going into internal energy, but on the other hand, there is a little bit of just sort of a push from the light or whatever the electromagnetic wave is. That's new. Like, make sure you get that what we're saying here. When light hits you, it pushes you a tiny bit. So let's talk about that. So this kinetic energy and momentum, that's this push that I'm talking about. So what that means really is that, in effect, it's a force, right? A push. I'm talking about a force here. So electromagnetic waves exert a force on anything that they hit. And this is called radiation pressure. Radiation pressure. So remember, force, let me just remind you that force divided by area is pressure. So pressure is force, but you're saying what the force is per square meter, right? That was what pressure was. And now we're talking about pressure from an electromagnetic wave, like light, and we call it radiation pressure. The word radiation here is just referring to any electromagnetic wave that's radiating from any source. Okay, and here's the formula for pressure from an electromagnetic wave based on the intensity of that wave. And what we have here is you take the intensity, you divide by the speed of light c is what it turns out to be. I'm not showing the derivation. And you multiply by a factor, which is 1 plus f. And what's going on here is f is the fraction of the wave that is being reflected. So remember, this wave that's hitting, we're ignoring any parts that just pass through. So we're just focusing on what gets absorbed and what gets reflected off. So this f can be anything between 0 and 1. It's a fraction, or a decimal that goes in here. So the idea here is, if this is being completely absorbed, if the wave, the light, let's just call it light, if the light is completely absorbed, then 0 of the wave is being reflected. So a 0 goes in there, so it's just a 1. So it's just I divided by c. So that would be like a black object, a pure black object that's not reflecting any of the light that's hitting it. The pressure is I divided by c. If it's reflected, if like a mirror, completely reflected, then 100% of the wave is being reflected. You put a 1 here, so that's a 2. So it's 2I over c. So the pressure is actually twice as much. And that makes sense, because not only is it hitting it, but it's actually also pushing off, right? So it's sort of like twice as much of a push when you don't just hit something, but you hit it and then bounce off. Okay. And now anything in between can also be covered by this formula. So if half the wave is reflected, it'd be a 1.5 here, right? So that's the idea. So let's do an example. So as in our previous example from class, we talked about how the intensity of sunlight, by the time it gets down to the Earth's surface, is about 1,000 watts per square meter. So what is the average force on an 8 by 20 meter roof that completely absorbs it? So if you recall, we had done the problem of, we figured out for this, it was the same setup, right? Sunlight hitting this 8 by 20 roof. We figured out the power that was being supplied to the whole roof, and then the electric field. So now we're sort of continuing, and we are now talking about the average force. So first we're going to figure out the pressure. By the way, I'm going to put a little like bar under my P here because we have a lot of P's going on. We have, of course, script P for power. I guess I haven't written it yet, but I've mentioned momentum, which is little p. I haven't written that down, though. And now we're bringing in regular capital P for pressure, right? These are all letters we've used before, but I don't know that we've used all three at the same time, so it can be confusing. This P is pressure. Okay, so pressure is, now if it's a roof that completely absorbs it, like a black roof, right, then that was where that 1 plus F factor was just a 1. So it's just I divided by C. Okay, so then we put the numbers in. So it's going to be 1,000 watts per square meter divided by 3 times 10 to the 8th meters per second, which is 3.33 times 10, 10 to the minus 6th newtons per square meter, which by the way is just Pascal. 3.33 times 10 to the minus 6th Pascal. That's a very small pressure, very small pressure. Okay, now that's the pressure, so that's how many newtons for every square meter. Now, so what's the overall force? To get that, we take the pressure, all right, and we multiply by the area. We multiply by square meters. So that's going to be our 3.33 times 10 to the minus 6 newtons per square meter times, and we have an 8 by 20, right? So 8 meters times 20 meters. And this ends up being 5.33 times 10 to the minus 4 newtons. So that's the force that sunlight is pushing down on sort of an average roof of a house. And you see it's very small, and this makes sense because this is why you don't really notice it and you don't feel like something's pushing on you when you're out in the sun, right? You feel the warmth, that's much more of an effect, but you don't feel the force. But it is there. It is there. It's just a small effect. Let's do another problem. So the average power of a laser pointer, so just one of those devices that people who are giving presentations use to, they press the button, right, and it shines a little laser, and you see a little dot on the wall, right? The average power of one of those is, let's say, 3.0 milliwatts, so it doesn't take a lot of power. And it shines a spot that's 2 millimeters in diameter onto a surface that reflects 70% of it, right? So maybe like a white, mostly whitish wall, something like that, or a not too dark wall. So what is the pressure that is being exerted on the surface? Okay, so the pressure is going to be I divided by C, and then since it's reflecting 70%, this is 1.70 times that. Okay, but what's the intensity? We don't know the intensity. So let's think about this. If we have the laser pointer, here's the button, right? And so it's shooting this out in a straight line. This is not a point source, right? Point source is where it goes out in all directions. This is just going out sort of as a beam, right? And then it's hitting the wall as a circle. So it's not spreading out. So the intensity is just the power divided by the area. Here's the power, and it's just divided, that power is just spread out over a small circular area, right? So it's going to be 3.0 milliwatts divided by, and then just a tiny little circle area. So pi times r squared. We have diameter is 2 millimeters, so the radius is 1 millimeter, so 0.001 meters squared. I'm just doing pi r squared here for a circle. Okay, and so that works out to be 950 watts per square meter. Notice that's close to the intensity of sunlight. This laser pointer is just a little bit less than sunlight. So I mean, yeah, if this number is correct, then that's what it comes out to be. And then we can take that and plug it in here to get the pressure. And this works out to be 5.4 times 10 to the minus 6th newtons per square meter. Or again, you could call that Pascal. That's what it is. Okay, so that's the answer. Now we're saying that these are very small forces, these are very small pressures, but there are some consequences to this that are sort of in the range of astronomy. So one thing is, if you think about the solar system and the sun is the main the main source of forces in the solar system, right? Everything, of course, is being pulled toward the sun via gravity, and that's what keeps all the planets and such in orbit. But now we realize, I mean, the sun is also putting out all this light at a certain intensity, and so we now know that that's actually pushing things away slightly. So gravity is pulling stuff in toward the sun, but radiation pressure is pushing it out. Okay, so a weird thing is that if you look out in the solar system, we don't find any dust. We don't find anything. We don't find any objects smaller than 2 micrometers in diameter. And that would be a little puzzling because, you know, we have big things, we have a lot of small things. There is a lot of dust and just small objects. You know, it's not all just huge planets. There's a lot of little things all floating around of all kinds of different sizes, and they're all orbiting around the sun. But weirdly, there's nothing that's less than 2 micrometers in diameter. Now that's pretty small, but at first there's no explanation for that. Why aren't there tiny pieces of dust, you know, just like there are, like, you know, in your house? Why is there nothing that size around in the solar system? And the answer to that is because of the radiation pressure. So gravity, right? Gravity is gonna the gravity due to the sun is going to pull on objects based on how massive they are. Well, how massive you are is based on your volume, right? It's based on how much space you take up. Your volume, of course, times the density of what you're made out of. So volume is, like, if we just think of spheres, volume is radius cubed or diameter cubed. I'll use radius here. So the force due to gravity is going to be based on how big you are radius-wise cubed. But the radiation pressure, the force that you feel from the radiation pressure, is not based on your volume. It's just based on your area, right? Because it's just like the side of you that's facing the sun that's getting hit by the light. So it's just your cross-sectional area. So it's just area. So that's just r squared, right? And if you just remember some basic pre-calculus, right? R cubed, so r squared is a parabola. R cubed is well, it's a cubic, right? And it actually starts out smaller and then it gets bigger. And so there's a place where they meet. And if you're smaller, if you're in this range, the cubed is actually smaller than the squared. So if you're small enough, if your radius is small enough, squared is more than cubed. So the radiation pressure is actually more than gravity. So I'll say that again. Radiation pressure is more than gravity if you're small enough. And so that means that even though this push from the sunlight is pretty small, if you were a tiny, tiny speck of dust, if you're small enough, that's actually more than the gravity that's pulling you in. Because you're so small, the gravity is going to be pretty small too, right? So again, at a small enough radius, you're actually going to be pushed away more than you're going to be pulled back in and kept in orbit. And so this explains why we don't see any dust smaller than a certain amount. It's all been pushed away. It was there in the very beginning when the solar system was formed, but it has been pushed away and it's gone now. It's been pushed out of the solar system. The radiation pressure, small as it is, was more than the gravity holding that stuff inside the solar system. Now, for most things that are bigger than that, right? R cubed is bigger than r squared, which means gravity is going to dominate, and so things are going to stay in orbit. Okay, but that's an interesting little tidbit, a fact, and it's explained by radiation pressure. Something else, which I think we mentioned last semester, is comets. So we always see comets, right? They've got this tail, they've got this stuff coming off, and it, you know, until you know better, you always assume that the comet is moving this way and the tail's like in the back, right? But that's not the case. That's only the case. Exhaust coming out the back is only true if you're in an atmosphere, in that there's, yeah, the stuff coming off of the comet, there's no reason for it to go backward out in space. So it's not moving this way, most likely. What is happening, though, is, I mean, this thing could be moving this way, or it could even be moving this way. But whatever the case, what the tail is doing is, the tail is always on the other side of the sun. So the sun is somewhere over here in this picture then. And the radiation pressure is pushing the little pieces of the comet that are coming off the comet away, right? The comet's big enough that the radiation pressure is not too big compared to gravity. It's the comet itself, but the little pieces that are flaking off are going to be affected by that radiation pressure more. So the tail of a comet is always away from the sun, and it has nothing to do with the way the comet is moving. Okay, one last application. Nothing to write down here, but some of you may have heard of space sailing. And this is an idea that has not been put into practice yet, but companies and NASA, governments are working on this, and it's called space sailing. And so, if sunlight can give you a push, the idea is if you had a very light, small craft attached to a really, really big sail, you could basically sail the sunlight. So the sunlight would hit this, right? And because force is pressure times area, if you have a big enough area, even a small pressure, you can get a decent sized force. And so you can actually use the sunlight to sail in the same way that boats use the wind to sail. And this has been studied, and in theory this should work pretty well. And so this is something that I think will happen in the not too distant future, is we'll be able to sail in space. Now, I'm not saying at first there'll be people on these crafts, maybe eventually in centuries from now, but yeah, there could be small whatever probes or whatever that can go to the ends of the solar system, and they will just they're being pushed out by the sun, and they'll just continue. The nice thing is it's free energy, right? It's just the sunlight is providing the power, the energy, and it'll just keep pushing, and so it'll just keep accelerating and accelerating. And the theory shows that these things will eventually get going really fast, really fast. So one more application of radiation pressure.